Section 6.5 is about assessing normality, which is where you take a look at a data set and try to determine if you think it came from a normal distribution or not. So the obvious way to do it at this point would be to use a histogram, right? That's a thing that we've already had come up, came up a couple of chapters ago. And there you think, well, you make the histogram, and if it looks like a normal distribution, like if it has a rough bell shape, then you'd say, okay, well then I think we can say this is approximately normal. Sure, that's one way to do it. The other way, which is the new way, is to use something called a normal quantile plot, sometimes referred to as a normal probability plot. But what you do there is you end up having to have some sort of software construct a graph, basically. We can have StatCrunch do it. They're easy to read because if things are working out the way that you want them to, what you're going to see is straight. So it'll look like a straight line. And so if you see something that looks roughly like a straight line, then essentially you're good to go. Then it looks like your data set's approximately normal. So what is a normal quantile plot? Well, it's a set of points that are plotted. So like with ordered pairs, like the way you normally plot points, where what you do is one of the coordinates is coming from the original sample data, typically the x value, and then the y value would be a z-score that's a quantile expected from the standard normal. So basically the way that it constructs the graph is that it lines up both of these in increasing order. So it puts your sample data in increasing order, and then it puts the quantile values you'd expect to get from a standard normal in increasing order, and then like the smallest gets matched up with the smallest, and the second smallest gets matched up with the second smallest, and at the end the biggest gets matched up with the biggest. And so why does this sort of complicated sounding thing give you something that's easy to read? It's because if you get a straight line, then it means the two variables have the same distribution. And we already know that the one on the y-axis is normal because those are coming out of a standard normal. So if you're getting the straight line, you go, oh, well then they got the same distribution. One of these is normal, so the other one's normal. So it looks like we're pulling data out of a normal distribution. That's basically how it works. So the procedure where if you're going to use one of these, I would say that if you have a histogram and you make the histogram and it looks normal right off the bat, I think you just go, okay, this looks fine. But then if it's something where you go, well, this isn't entirely perfect, or maybe it looks good if I use this bin width, but if I use this other bin width, it looks a little weird, something like that, then maybe that's where you want to take the step and use the normal probability plot or the normal quantile plot. So you'd say, okay, well, if the histogram is a little bit off from the bell shape, then maybe we're going to take this step here. And I guess going along with that you don't have too many outliers. So this idea about rejecting normality if there's more than one outlier present, that's because if you're getting multiple outliers, especially in the same direction, then maybe that's an indicator that the shape is actually different and those outliers are part of the shape. So maybe it's something like if you have a couple of outliers that are really big, but kind of spaced out from each other, maybe that means that really you've got something that's right skewed and your sample was such that you just didn't get very many values out in the tail. So that's where you go, okay, if we're getting multiple outliers, that's kind of weird looking. And maybe right from there you can say, okay, this doesn't really look all that normal. But with the normal quantile plot, you would not want to make one by hand. I guess theoretically you could, but it takes forever. You want to use software here. So StatCrunch can do it. That's what we're going to do. So if what you get looks like a straight line, and there's not some systematic pattern that's not a straight line, because if you have some other kind of specific distribution like a uniform or something like that, I think with a uniform you get a thing that kind of looks like an S, but it's really subtle. And I think we're going to see that. I think it's on the next page. But usually what happens is you don't have some specific other shape. You just have something that's not normal. And usually if the normal probability plot doesn't look the way you want it to, you get things that look like this, where this thing right here on the right, that's got like sort of a bend or an elbow, like right there, basically. So that's usually what you get if it doesn't work out. you get like a bend or an elbow in the graph where like that's really steep and then all of a sudden it levels off a lot. That's usually what happens, and that's an indicator that you have a skewed distribution, basically, when that's going on. So the thing on the left is what you really want, and that one's perfect. I mean, I picked the sample values out of a normal, like I had software randomly generate them. So yeah, that one looks absolutely perfect. They don't usually look quite that good. They tend to look close to that, except maybe the ends are a little imperfect. But if you get something that's generally a straight line, that's what you want. But usually if it fails, you get the bend like we're getting right here. All right, so from our book, so this is something that looks pretty good to begin with, although not perfect, right? Because you go, okay, here's the peak, but then, you know, like this one's a little taller than that one's a little taller than that one, right? So you go, it's not perfect, but it looks close to normal. And then if you look at the normal probability plot, see, it pretty much follows this line, except at the ends you get, you know, a couple that are straying a little. And that's okay. So this is what you get usually for one that's approximately normal. So you don't get that perfect thing like I had on the last page, right? You get, you know, these strays like down here, or like I'd say that's a stray up there. But here, this is one where you'd say, okay, for the most part, except for like a couple of points on the ends, this looks pretty good. So this is one where you'd say it's close enough. So just looking at that last sentence, where it's safe to assume that these IQ scores are from a normally distributed population, right? So you're not looking for it to be perfect, although that would be great. Close enough is good enough. All right, well, what about if you have a uniform, which is what that is? So that's something that's symmetric, but it's not normal. And notice what you get. Like, just look at where the blue dots are. It's not straight. It's kind of like an S shape. Kind of a subtle S shape for the most part, although I guess it's getting more pronounced as you get toward the ends of it. But that's not straight. So that's one where you'd look at it and go, that has a pattern, but it's not a straight line pattern, right? It kind of looks like an S. So not a straight line pattern, not going to be normal. Okay, about this one. This is what I'm talking about, where you've got one that's heavily skewed, right? I mean, when you look at the histogram, I mean, this is one where I think the normal quantile plot is probably redundant, because I don't think anybody would look at this graph and go, yeah, that might be normal, right? Like, that's not happening, right? Everybody's going to look at that graph and go, no left tail, stretched out right tail. Even though almost everything is in this first big bar, there is a stretched out right tail. Like, this looks right skewed. And that's exactly what you get. And really, I put this one in here just to illustrate, like, yeah, this is what happens when you have a skewed distribution, a heavily skewed one. And here you got the elbow, right? Because it's almost straight up and down, like through here. And then all of a sudden, it flattens way out. And there's a best fit straight line thrown in there, which clearly does not match up with the pattern of the dots. And that's kind of the point, right? That this is not a straight line pattern whatsoever. So this would be something where you'd go, yeah, that's clearly not normal. All right, so how do you do this in StatCrunch? I guess that would be the big question. So what you want is, if you go to the graph button, there's something called QQ-plot. So it's maybe not what you'd necessarily expect it to be called, right? Because I think you expect it to be called maybe normal quantile plot. That would be kind of natural. QQ-plot is actually a more general term, where the QQ just means quantile. So you could really do it for like any two samples to see if they have the same distribution, right? Because then that general idea makes more sense. That's not really what we're going to use it for. So that just means that in order to make it a normal quantile plot, there's a box you have to check, which is in step 4. So to go through an example, or really a couple of examples of how this works. So this sunspots CSV file, I've got it open already. It's right here. So there's all this sunspot data. I think there's quite a bit, actually. Oh, yes. There's a lot of sunspot data. How far does this actually go? Okay, 2,820 observations. That's quite a few. So I'm going to take this. I'm going to copy it. I'm going to put it into StatCrunch, which I have open here. So copy it right there. And I copied it into the heading so that way sunspots would show up in the heading and not in one of the rows where the data is supposed to go. All right, so then what you do is you go to graph, and then QQ plot's one of the options. It's down here. So if I click on that, then I want to select my column where my data is, which is the sunspots column. And then if you just click this box right here for normal quantiles on the y-axis, then that should do it. So then if I click compute, there we go. So you look at that thing and you go, well, that doesn't look great, right? That looks like it has the elbow. So that one doesn't look like it works, right? That does not look straight at all. So I guess going back to where the example is. So does the data, which I guess I really should say do the data, since data is plural. I've got a grammatical error there. But do the data appear to be normal? I got to go back and fix that. I feel kind of embarrassed now. But it would be no because of that bend, right? So you'd say no, since the graph in the normal quantile plot, so normal quantile plot, contains an obvious bend. So contains an obvious bend. Right? That's certainly what we had. If I go back to it for a second, right, that is not straight. And I guess just for effect, let me close this one out. And what if I wanted to make a histogram out of sunspots? Let's see what we end up with. Yep, right skewed. Because when you get the bend, that's what you expect, is that your data was probably skewed to begin with. And that's exactly what this looks like, right? This is all right tail. Okay, so that's the first one. The second one, which if I go back to it, there are data sets that go along with our book. So I can show you where they are. Let's see, that's why I have this open. So there's our book right there. I don't know how they suddenly got to the 13th edition, but they did, because ours is the 6th. But if you go there, and then if you go to download data sets, and then Excel, they're going to show up. And I guess this will, yeah, it'll give you the zip file, and then they're in there. Because then, there they are. So we want this 15 presidents one, which I actually have open already. It's right here. And it just has all the presidents with how old they were when they were elected. So then that's basically what we're looking at, because we want age. So we're going to copy age. So I'm just going to select the column heading and then Control C. And then let's see, if we're going back to StatCrunch, I don't need this anymore. So I'm going to delete that column. And then I'm going to paste the age one in there. And then make the QQ plot. So graph down to QQ plot. Then if we go to age and then normal quantiles, compute, there. Not too bad, right? So that one looks pretty straight. And I guess we should probably also check the histogram. So let's see if we make can we make both and have them both as pop-up windows at the same time? I think we can. Yeah. Okay, now we can have them right next to each other. Okay, so you look at that one and you go, yeah, that looks ridiculously symmetric. Just look at that histogram. And I think if you were going to go through the progression of graphs, if you graph the histogram first, you'd go, yeah, we're fine, right? I don't even know if you need to take this next step. It's good to know that it's there for the ones that are kind of iffy, but this one's not really iffy, right? I mean, looking at this thing, you go, yeah, it's almost perfect. But then you look at this and you go, yeah, that looks pretty good too. That looks pretty straight. So to go back to the question, does the data or do the data appear to be normal? Yeah, that one looks good. So we can say that, we'll just say this one is pretty straight. So it seems reasonable to say that the distribution is approximately normal. Right, it looks like that makes sense. We had a normal probability plot that looked pretty straight, or normal quantile plot, whatever you want to call that. And then this thing looks great. So yeah, I think we're good, right? Like those, they look the way that they're supposed to look. So that really is the only thing in section 6.5 is the normal quantile plot. So this is kind of a short one. The biggest thing I think is how to make them in StatCrunch, and then what they actually are. How it's got the normal quantiles on one axis, got the data on the other, and then if you get a straight line, it just means that the distributions match up. So then you can say that your data looks like it comes from a normal distribution.